Good morning, dear students. I am Vinod Seni, your physics teacher. This is our first video lecture for the chapter of electromagnetic waves. In this video, we will learn about the Maxwell equation and the Maxwell's correction in Ampere's equation. Dear students, I expect you are familiar with the electric and magnetic field. If you want to get an overview of electric and magnetic field and Gauss law for electric field or electrostatics, then you can watch this video. The link is given in the I button above. First, the Gauss law for electric field, we know it very well that the electric field flux which is passing through a closed surface is given by the electric field dot area vector, its closed surface integral. It will be equal to the total charge which is enclosed by this surface, divide it with epsilon naught, which is called the permittivity of the medium. If that is air or vacuum, then it is denoted by epsilon naught. For the magnetic field, the Gauss law can be written as closed surface integral of magnetic field B vector dot area vector. It is equal to 0. It shows there is no existence of a single magnetic pole. Dear students, if there is a closed surface in which there is no charge or magnetic pole enclosed, in that condition, the first Gauss law, which is for the electric field, it will be converted now into E vector dot dA vector is equal to 0 because the total charge enclosed in this surface is 0. In that condition, these two equations are very much similar to each other. That is the beauty of physics. James Clerk Maxwell was the first scientist who have tried to find the mathematical similarities between electric and magnetic field. The one more equation which is called the Ampere's equation. According to that, the line integral of magnetic field B vector dot dl vector over a closed loop is equal to the permeability of the medium times the total current passing through this loop. This is the arithmetic sum of the all currents passing through this closed loop. But if there is a single current passing through this loop, the loop is here. If a single current passing through this closed loop, this current is written as I, then we can write this Ampere's equation in this form mu naught I. This I here denotes the rate of charge passing through a cross section of this current carrying wire or this loop. Dear students, this is the Ampere's equation which is related to magnetic field. But according to the Faraday's law for electric field, E vector dot dl vector, that is the line integral of electric field over a closed loop, it is equal to minus d phi b upon dt. Phi b is the magnetic field flux which can be calculated by that is magnetic vector dot area vector. Now dear students, this is the second equation, this is the third equation, this is the third equation, this is the fourth equation. These two equations in first and second are very similar to each other, but there is something missing between the similarity of equation 3 and 4. This Faraday's law is showing that due to change in magnetic field flux or change in magnetic field over some volume or area, there will be some electric field produced. James Clerk Maxwell tried to find the similarity, and according to his study, there must be a term in equation 3 for the change in electric field flux. There would be magnetic field induced. Now dear students, this is called the induced electric field for the change in magnetic field. Here is a circuit which is showing that a capacitor, which is parallel plate capacitor, it is connected with a battery. One key is introduced between them for opening and closing this circuit. Now dear students, when we close this key, this capacitor will start to charge. This is the plus terminal of battery, which is shown by the bigger line. This is the negative terminal of this battery, which is shown by the small line. On the left plate, there would be plus charge deposited, but it will be varying with time. When the key is closed, it starts to charge. In a small time period, it will be increased gradually, and when the key is opened, then this capacitor will start to discharge. During the process of charging and discharging, there will be some magnetic field induced in the space between the plates of capacitor. Now dear students, the current is flowing from the positive terminal of battery and it is incoming into the negative terminal of battery. When a conduction current is flowing in a current carrying wire, there would be some magnetic field induced, and if we place a magnetic needle near to it, then there would be deflection in the magnetic needle, which was the experimentally proved by Ørsted. He was the first scientist who have tried to find the magnetic effect of electric current. So when this key is closed, this magnetic needle will be deflected. When this magnetic needle is placed on this side, then also this deflection will be observed. But what will happen if the magnetic needle is placed in the space between these parallel plates of capacitor? According to the experimental observations, when this key is closed and when it is opened, there deflection in the needle will be observed. What is the reason of this deflection in magnetic needle? Here is a conduction current flowing in this current carrying wire. Here also a current is flowing in this current carrying wire, but there is no electric current between these two plates. What is there? There is an electric field produced between these two plates. We have learned the electric field between the capacitor plates is given by E electric field is equal to sigma upon epsilon naught. Sigma is nothing but the surface charge density. Sigma can be written as sigma is equal to charge Q upon area. The charge Q is total charge on a single plate of capacitor. Then we can write the electric field between these two plates is equal to charge Q upon area epsilon naught. This is the first part. Now dear students, we are trying to find out, according to Maxwell, what is the correction which was needed in the equation 3 for its perfection and completion. Students, on the plates of capacitor, the charge will be increased gradually when we close the key, and when we open the key, the charge will be decreased gradually. In that condition, the charge will be changed, so electric field also will be changed. यहाँ इस सर्किट में जो कैपेसिटर की दोनों प्लेट्स है उनके बीच में इलेक्ट्रिक फील्ड होगा और वो इलेक्ट्रिक फील्ड की लाइंस एक दूसरे के पैरेलल होगी। यहाँ मैग्नेटिक निडल रखने पर जब वायर में करंट फ्लो होता है तो उससे मैग्नेटिक फील्ड जनरेट होता है, लेकिन यहां प्लेट्स के बीच में अगर आप मैग्नेटिक निडल रखते हैं और उससे अगर डिफ्लेक्शन वहां पर ऑब्जर्व होगा, देन देयर मस्ट बी सम एक्सप्लेनेशन अबाउट दिस डिफ्लेक्शन और देयर मस्ट बी सम मैग्नेटिक फील्ड which is causing this deflection in magnetic needle. Now dear students, this is the formula for electric field between these two plates. जैसे ही आप की क्लोज करते हैं तो इलेक्ट्रिक करंट यहां कैपेसिटर प्लेट्स पर चार्ज डिपॉजिट करना स्टार्ट करता है और चार्ज का इंक्रीमेंट धीरे धीरे होता है। उस चार्ज इंक्रीमेंट के दौरान इलेक्ट्रिक फील्ड में भी चेंज होगा। अकॉर्डिंग टू द मैक्सवेल ऑब्जर्वेशंस, he have written this equation like this. The equation third will be converted now into B vector dot dl vector mu naught I. This is the conduction current. There must be another current. We write it as ID. This ID is nothing but the deflection current. This is the important term and most significant topic of this video. What is the displacement current? This is the term which will be related to change in electric field. Now dear students, write it as equation second. The electric current, which is conduction current, it is given by rate of change in charge from a cross section. We can write it as I current will be equal to change in charge. So get the expression of charge from here. It is equal to EA epsilon naught. The Q is E A epsilon naught, write it from the equation 1. This is divided by dt. Now this term will show the electric current which is related to the change in electric field, but there is no charge flowing from one plate to another. ID can be written as epsilon naught dEA upon dt. What is EA? This is nothing but the electric field flux. The electric field flux phi E can be written as electric field vector dot area vector. If these both are in same direction, in that condition it is written as EA. Now dear students, this equation ID can be written as epsilon naught d phi E upon dt. This is the important term which is showing the displacement current. Why it is known as displacement current? Because in reality there is no current flowing between these two plates of capacitor, but this is the current which is explaining the induced magnetic field between these two plates due to change in electric field. This is called the displacement current. Now dear students, we will replace this term ID in this above equation second, and we will get the final expression after the Maxwell's correction. B vector dot dl vector, it is equal to now mu naught IC. This is the conduction current which requires the flow of physical charges in current carrying wire or a conductor, and the second term will be written as mu naught epsilon naught d phi E upon dt. This is the Ampere's equation after the Maxwell's correction. This is one condition which we have observed here, but this equation will be applicable in any kind of electric or magnetic field induction. This is the final equation of Ampere after the Maxwell's correction. Now dear students, we will get an overview of Maxwell's equation, and we will get an overview about the information we get from these equations. James Clerk Maxwell tried to find the unification between electric and magnetic field phenomena, and he was enough successful in his practices. The James Clerk Maxwell only find out this correction in Ampere's equation. All these four equations were available before him, but he tried to make a complete package of equations for the explanation of electric and magnetic field phenomena. After this Maxwell's correction in Ampere's equation, this equation is now known as Ampere-Maxwell's equation. Now dear students, I suggest you all to please pause this video and note down all these equations and mathematical terms and this derivation also for your further reference and practice purpose. Dear students, I will write here the Maxwell's equation and will try to explain you the physical significance of these equations. This is the first equation which is known as the Gauss Law. E vector dot dA vector, the electric field flux passing through a closed surface, it is equal to the total charge enclosed upon epsilon naught. After the modification, this equation will be converted into gradient del vector dot d vector. D vector is here. D is equal to epsilon naught E. Del dot d vector, it is equal to rho. For you, it is enough to know this is the first equation of Maxwell, which is from the Gauss Law for electric field, which was based on these experiments in which we found that the similar charge repel each other, the opposite charge attract each other, and also the electric field is produced due to the charges. The total electric field in some region is equal to sum of the electric field generated by individual charges in that region. Now dear students, the second equation, which is very similar to this first equation, but this equation is related to magnetic field flux B vector dot dA vector, it is equal to 0. It is the Gauss law for magnetic field. This is the second Maxwell's equation. The third equation is nothing but the Faraday's law for the line integral of electric field or the induced electric field due to change in magnetic field flux. According to the Lenz's experiments, the induced electric field will oppose the change in magnetic field by which this electric field is induced or electric potential is generated. It will oppose the change in magnetic field or change in magnetic field flux. This is the third Maxwell's equation, which is Faraday's law. It's showing the line integral of electric field over a closed loop. It is equal to negative rate of change of magnetic field flux. The fourth Maxwell's equation is now known as Ampere-Maxwell's equation. According to that, the line integral of magnetic field over a closed loop is given by permeability times the conduction current plus the displacement current, and displacement current, when replaced by its expression, this equation will be converted into mu naught IC plus mu naught epsilon naught differentiation the rate of change of electric field flux with time. This is the fourth Maxwell's equation. This fourth equation is showing that due to change in electric field flux or change in electric field, the magnetic field will be induced. The displacement current ID can be written as epsilon naught d phi e upon dt. If we use this notation, d is equal to epsilon naught e, then we can write it as id is equal to d epsilon naught ea upon dt, or id is equal to the differentiation d, capital D, a upon dt, or we can write it as id, the displacement current, it is equal to d phi d upon dt. This is the complete explanation of this Maxwell's correction over Ampere's equation, and these are 4 Maxwell's equations and their overview about their applications and formulation. Dear students, I suggest you all to please pause this video and note down all these equations for your further reference and practice purpose. I will give you 5 problems for your practice. Try to solve them. If you have any doubt about their solution, please write in the comment box. If you like this video, please like it and share it with your friends. I thank you all for watching this video till the end. If you are new at this channel, please subscribe this channel to get the notifications of latest update, and don't forget to tap on bell icon and opt for all notifications. Keep learning, keep practicing. The problem solving is always a fun. Thank you.